We are given this scenario. A family is off on a hike, having left their leftovers out on a picnic table. A colony of fire ants 600 feet due north of the table detect food and begin their march traveling at 4 feet per minute. At the same time, a colony of black ants 800 feet due west detect the food and begins their respective march traveling at 5 feet per minute. The first thing it asks us to do is find how long it will take each colony of ants to arrive at the picnic table. Since this question is asking how long it will take each colony of ants to travel a specific distance, we have to use the formula distance equals rate times time to answer. Since we are trying to find the time, we need to convert our formula into time equals distance divided by rate. The fire ants traveled a distance of 600 feet with a rate of 4 feet per minute. To find the time, we divide the distance, 600, by the rate, 4, to get 150 minutes. The black ants traveled a distance of 800 feet with a rate of 5 feet per minute. Again, we divide the distance, 800, by the rate, 5, to get the time, 160 minutes. Next, we are asked to write a function that models the distance between the two ant colonies at any given time. Because the two colonies are coming from the north and the west, distance between them can be represented as the hypotenuse of a right triangle, or C, in this diagram. Now, to find this distance C, we can use the Pythagorean theorem, or a squared plus b squared equals c squared, with a being the fire ant's distance from the picnic, b being the black ant's distance from the picnic, and c being the distance between the two colonies at any given time. To find the fire ants' distance from the picnic table at any given time, we take their maximum distance away, or 600 feet, and subtract 4 feet times the amount of minutes they have been traveling. We use the same method to find the distance b at any given time. We put these values a and b into our formula, a squared plus b squared equals c squared, and then take the square root of everything in order to isolate c, or the distance between the two colonies at any given time. The third and final question asks us to determine at what point in time the two colonies are 500 feet apart from each other. In order to do this, we need to plug our function into a graphing calculator. To set the window, we need to find reasonable x and y values of this function. The x-max is time, and we know that the most time it took was 160 minutes for the black ants to reach the colony. So when they're 500 feet apart from each other, it's not going to be nearly as much. So it's probably going to be less than half. So we'll try 100 to be safe. The y-max is 500 because we're trying to determine the distance, which is the y values, that they're apart from each other, which is 500. So we'll set it a little over 500 to make it easier to see. We also should set a bar at 500 so that we know where our function is going to be hitting y equals 500. Next, we can graph. We see that this point of intersection is where the time is equaling that 500 value. We'll go second calc and then intersect to find the precise x value for this y value of 500. The calculator gives us an x value of 78.16 minutes. We can convert this to just 78 minutes is when the two colonies are 500 feet apart.